like I was mentioning, we're going to get into some more real-life functions with this. And so our example here that we're going to start with is going to be a 4-hour fundraising pledge drive. The students organizing count the money raised at the end of each hour. So they don't know constantly what their total is. They just total at the end of the hour. So, how much money had the students raised after 2 hours? So here's the thing on graphs like this. The open circles are like, there's just a hole there. So when I get this, that's not really there. I'm going straight through it. And I'm going up to where the circle is closed. And whatever that value is, I just follow back over here. And I'm set. So we're only looking for closed dots. How much money did they raise in all? You're like, okay, we're probably going to be looking for the highest dot. So I find the highest dot. I just follow it back over. Again, not a lot of calculating with this, just a lot of kind of reading what's there. But this is the part of step functions that gets a little weird. If x is the number of hours the drive have passed, then the function shown by the graph gives the number of dollars raised. Okay, what is f of 3.5? All right, so here's 3.5. If I follow that up, there's no like dot per se here, but that's the value. So here, if I follow it back over, we're right in between 14 and 1600. So here's the weird part about step functions. They don't count till the end of the hour. So like for instance here, they had $1,500 at the start of hour 3. Like according to this data, they didn't make any more money at all until the start of hour 4. We know that's not true with their pledge drive, but that's how they're choosing to calculate it. That's where these steps come from. So, on what interval notation, does f of x, y, equal 400? So I look right there. And I'm like, okay, so it's $400 between hours 1 and 2. But the dots matter. Closed is your bracket, and open is your parenthesis, which again just tells us at hour 1 it's starting and includes 400, but at hour 2 it's not just going to be 400, because at hour 2 with that parenthesis it tells us that's when the recount was. And so we don't get confused on which part that is. And then domain and range. Domain, your least to greatest on your x. I have actual values for how much money I've raised at both the beginning and the end. That's why I'm using brackets for both and not using a parenthesis for either when I do that. And my range is just my bottom to my top. So again, I'm looking at the lowest point, I'm looking at the highest point, and what values are represented with those. So you can get several values that's the same exact y, or f of x, for the x. Like if you ask, well, what's f of x at 1.25? 400. What's it at 1.5? 400. What's it at 1.99? 400. So step functions are a little bit different as far as that goes. Definitely not one-to-one, but absolutely pass the vertical line test. So that's kind of what we're looking for if we're given something like that general. But what if? Oh, what if? What if we are given a system or an equation and we have to graph it? Okay, there's a couple of ways to try and tackle this, and And it just kind of depends a little bit. So the greatest integer function, which we can get these on the calculator, the greatest integer less than or equal to x, called the round down function. So our domain will always be infinite because it's just going to keep going. And the range will depend on the parent function. We'll get that verbiage in here in a minute. So round down. I hesitate to say it's like absolute value. It is for some of these. If you get a whole number, okay, the whole number is going to stand. So f of -3, if it's this round down function, kind of check through the first couple. Then if we need to clean some stuff up, we will. If it's a whole number, you just leave the number. You don't make it positive. You don't do anything else. You leave it. But if it's fractional or a decimal, here's how I would prefer to look at this. If you were to be looking at a number line, so I'm just going to take a moment here. Okay, so I have a number line. F of 2.5. Okay, here's 2.5. If you round down to the next whole number, what would that be? 2. So we go with 2. That's all you're doing for any of these. F of -1.8. If you round down to the nearest whole number, what would it be? -2. So here we mainly have to worry more about positive and negative, how we think about those, as the number line would go. But otherwise, it's nothing too bad. Let's see, f of 1/2. Round down, where do we end up? 0. -1/2 round down. -1. This round down function is going to cause our steps in our step function. That's just where they're coming from. And so when we're asked to graph the step function, okay, what we're going to do, let me get this out of the way for a minute. Okay, graph the step. Remember, f of x is just a fancy way of saying y equals. So if x is between 0 and 1, the y value is 1. So between 0 and 1, or equal to is a closed dot, just less that is open. So y is 1. When x is 0, it's filled in. When x is 1, y is still 1, but it's an open dot, and we connect the dots. And then we move up to 2. Because when x equals 1, y equals 2. And the bar goes to the next spot, again, which is an open circle because it doesn't have or equal to. And so basically all you're doing is, so my one's on the left, when x equals 2, y equals 3, but it's or equal to, so that gets a closed dot. But the one on the right that makes my step is going to be open. When we get to y is 4, we start at 3. And you notice there's no gaps. What I mean by that is wherever you start, you go over, and when that hole comes where you normally fall down, it's like you're getting beamed up by a UFO here. You get over, it's like, whoop, up to the next step. And then you're about to fall, nope, whoop, sucked up to the next step. And you just keep doing that infinitely. That's why your domain would be infinite, because the steps are not going to stop. I could extend that this way if I wanted to as well. It's a little trickier sometimes when the values are all different like this, instead of just giving me the round down integer, which I'll show you here right now. But it might even be beneficial when you get to these to start doing something more with a chart of some sort. So, for instance, when I look here, I'm like, okay, so 2x, 1 is less than x is less than 4. Okay, so what's that going to mean? So if I was doing this, and this is the other thing that's weird with mathematicians, these are saying the same thing, okay? These are both the round down, the greatest integer function, which is odd, but hey, it is what it is. So we're going to start this one at 1. And if you plug in 1 for x, you get out 2 for y. So 1, I go up to 2 for y, and I close my dot. And so I notice this is going to be going up to 4. So if I do this with the whole numbers up to 4, and again, this is just while I'm getting used to it, I'm going to show you some patterns that you can use too on these. If I plug in 2, I get 4. If I plug in 3, I get 6. We're just multiplying 2 times my x value. Those are going to be the spots where your closed dots are. So 2, 4, and of course I did not make my graph large enough, but we're gonna wing this as best we can. And so to make the connectors now, instead of just drawing a line through it like it's linear, which it's not, we start here and we make our bar until we see the next closed dot, and we put an open so we get whoop, sucked up to the next spot. And then we put a bar whoop, up to the next spot. And again, this could go infinitely. But I was told to just do it between 1 and 4, and then oh no, that's right. I should have just stopped here technically, because the 4, that would be a closed dot normally, but that's one of those details that we do. But here's the nice thing about it. If I just gave you the equation y equals 2x, you'd have a y-intercept at 0, you'd go up 2 and over 1. Up 2 and over 1. So in reality with these, you're doing a line. This is linear. Just instead of connecting the dots and making a line, you're making these bars that create steps. But what you are able to do, let me show you on the calculator in case you want to double check something sometime. So if we go to y equals, this will be kind of interesting. We might have to change one setting, we'll see. You're like, okay, Hardy, how do I put this in? So once we're ready for it, we're going to go to Math, Numeric, and then INT, which is greatest integer function, which is number 5. So Math, Num, there's number 5. So it just says, it's not like the absolute value where it actually changes something. It says int, and then it has this parenthesis. We're just going to type in whatever we have there. So in this case, it's just 2. And then we'll close that up. And so if you graph it, you're going to see all these little, it's not going to look like a line, it's going to be all these little bars that are going across, sort of in that same slope that you see here. If you want to look at points, you can look at your chart, and again, check this out. All the numbers that you see in your chart, just like we did with the chart here, are all of your closed dots. And then you're going to keep that line going until you get to the next point. And then those keep going. But do not connect these vertically. Okay? There's just steps. Nothing vertical. Everything is going to be horizontal that we do when we're working on these. But if you can graph a line, you can do these. For instance, let's say we're doing 15. Let's see a little bit of mix here. So I look and I'm like, okay, absolute round down for x minus 2. All right. So if I think about that for a minute, I could make a chart for myself, but let's use the calculator again here. Because I think once you see how this pattern develops, we might not even need this. So math num number 5, because we're starting with it right away this time, x minus 2. So I look and I'm like, okay, let me pull my chart up for this. Here's what I want you to notice. All right, we're going to put a little chart over here. And we'll start at 0 again. I'm just going to start with those 3 points. Actually, I'll do one. So 0, -2, 1, -1, 2, 0, 3, 1. Okay, I can keep going as big as this graph goes if I wanted to. And all I'm going to do, no matter where I'm at, wherever that closed dot is to the left, we're just going to keep this non-stop step system going. The closed dots, we make a bar, we put an open dot on the end, and we just roll. Here's where you can simplify it, though. Look at just the filled-in dots. If those weren't there, if that was just y equals x minus 2, means your y-intercept is at -2. Coincidence. And your slope is 1. 1 over 1. 1 over 1. This is literally just the filled-in dots. You just have to make the little pieces that go with. That's going to be true for all of these. Now, let's just check and make sure, again, that I'm not blowing smoke. I never would want to do that to you. So I look and I'm like, well, what if we did, this is kind of different. What if we did this one? So you're like, okay, well, let's try the Hardy theory out. If this is just -2x plus 3, okay, so there's my y-intercept. And I'd go down to an over 1. I put a dot. And I'd go down to an over 1, down to an over 1. This gets us an idea. And so then I should just make, again, until I see the x value of the next filled in dot, I'm just making these little bars. But let's see, is there like an exception to the rule? Is there something else I need to be careful of? Let's check this out. Looks like the intercept is at 3. Let's check the chart. 0, 3, 1, 1, 2, -1, 3, -3, and we're off and running. So even if it's negative, it just runs like slope and graphing a line. What if, bless you, well, what if like all this stuff is in the round down? Like, does that change it? Like if it's inside instead of outside? I don't know. Let's find out. Math, no. All right, I'm just going to use 0.5 instead of putting a half because I don't want to mess with all these extra parentheses. Close it, because that's the only part we're taking the greatest integer function of. Okay, so let's see. So this should be a little bit different. Ooh, longer steps because of this different slope. It stretches more. But let's get down to business. You're like, ooh, now this is kind of weird, Hardy. Like, why am I seeing double zeros, double ones, double twos? What's that deal? So let's do this like it was a normal line. Up 1 and over 2. Up 1 and over 2. Down 1 and left 2. Because again, my slope is a half. So notice, this time to get bar-wise from dot to dot, your bars have gotten longer. So let's compare now between what we just did, doing what we know about lines, and how this greatest integer function works. Does this work or not? At -2, my y value is 0. That's true. At -1, my y value is still 0. That's true. When I get to 0, whoop, I'm up to 1. When I'm at 1, I'm still at 1. When I get to 2, whoop, I'm up to 2. At 3, I'm still at 2. When I get to 4, whoop, I'm up to 3. It doesn't matter if your lead coefficient is in the greatest integer or it's not. Just graph the line and put the bars on. Keep it simple. Keep it as simple as you can. Okay? So if you need a reminder, or maybe you didn't write this down when we were doing it originally, just as an FYI, on page 15, okay, the button pressing is all there. But again, I don't think you're going to need this if you just know how to graph a regular line that's in slope-intercept form. I don't think it's going to cause a problem. So, with the 10 bajillion things I've already talked to you about this period, okay? You know the drill. Odds at a minimum, check your answer. Oops, I'm in the wrong section. Hang on. Back up, Hardy. Back up. You're to next week already. Try again. 7 and 8. Answers are over there. Do your odds. Check things as you go. And actually, am I gonna? I am, because I know I'm going to get a question about it anyway. Hardy, what, pray tell, is going on in number 11? Because I've never seen a graph before that has, what is this, 2 y-intercepts? You know, how does this work if it doesn't look like a regular equation? How am I supposed to do this? Okay, let's experiment one more time. So page 7, we're going to look at number 11 here. We're going to put it in the calculator, and we're going to see if we can find a pattern to this one like we have the others. We want to work smarter, not harder. Okay. What I'm interested in is, where is my y-intercept at? So I go in. My y-intercept is at 1. Okay. So if that's true, let's put some of these points in. 0, 1, -1, 0, -2, -1, 1, 2, 2, 3. Okay. So I look at that. And so if I went to the calculator, I know this is just going to go like this. But what if I didn't want to go to the calculator? How could I deal with this? Well, this looks like y equals x plus 1, because that's where the y-intercept is, right? So if I was in slope-intercept form, This is y equals x plus 1. Check this out. What's negative 1 plus 2? 1. So you're like, wait. So if there's extra stuff going on here in my brain, I can just combine like terms and treat that like it's y equals x plus 1. Make my filled in dots and connect the bars? Absolutely. 100% is what's going on with that. So when you do 13, just combine the 1 and the negative 3, make your dots and go. Keep it simple, okay? This is a nice assignment just because